Hi everyone and welcome back. It's Kira Garfola with Greenville Tech's Math 109. Today we're going to be talking about section 6.2, which is modeling with cubic and quartic functions. This is a relatively short section, so I'm sure you'll be relieved, and you'll see that a lot of it isn't really that new of a concept. So it's nice in the middle of our last unit, right, to have a little bit of a break. So remember that we've already talked about modeling data in several contexts. We've talked about linear modeling. That was the first one that we did. And that was when we found that linear regression, that straight line fit. And we looked there for constant first differences. Remember, if those first differences were exactly equal throughout the model, then we had a perfect fit. And if they were approximately equal, then we had an approximate fit. We also talked about quadratic modeling, where our data looks like that parabola, right? Or at least half of a parabola, depending on the domain of the data. Here, we knew that that was a good fit based on the constant second differences. Again, if they were exact, then it was an exact fit. If they were approximate, then it was an approximate fit. And then in the last unit, we did exponential and logistic modeling. And for exponentials, we had looked at that constant percent change, which is that percent change in your second differences. Today, we're going to focus on higher degree polynomial modeling. And remember that a higher degree polynomial is higher than degree of 2. So we're going to talk about x cubed, x to the 4th, and so on. So first, we're going to talk about cubic models. So we can make a cubic model by fitting a cubic polynomial function to the data. And remember that a cubic polynomial function takes the form of x cubed plus x squared plus x plus a constant. All of those have their individual coefficients. And the important thing about the coefficient on x cubed is that it cannot be 0 because we need to have that x cubed term. To know if our cubic model is appropriate, we need to look at these third differences. So we're going to take the differences of these second differences to get the third differences. Just like before, if they're perfectly equal, then you're going to have an exact fit. More likely in real data, they're going to be an approximate fit. So they're going to be approximately the same. Remember that our third differences are differences between consecutive second differences. It's just an iterative process between the differences. Luckily for us, we're going to use our calculators to fit these models. We're not even going to attempt them by hand. In our TI calculators, you're going to go to the same place that you've been when you've been modeling data, except now you're going to choose cubic reg. Let's look at an example. In this table, we see the number of Americans in millions who worked full-time based on their age in 2012. So it's a little bit older data. We want to find a cubic model for f of x, where x is the age and f of x is the number of Americans who worked full-time. So here, our top row is x and our bottom row is f of x. We want to put that information into our calculator. Remember in L1 and L2. So in L1, we're going to have our x values. In L2, we're going to have our f of x values. And then we're going to go to calc, and we're going to choose cubic reg. It should be right below your quadratic regression. So remember, we've done linear, we've done quadratic, and now we're doing cubic. And when you choose cubic reg, you're going to choose your data. Again, you can store them with y bars and things like that. You're welcome to store them if you want to plot them together. But the important thing about the model, at least for this problem, is to get your answer out. Here we see the A is our coefficient for x cubed, so negative 3.616. Be careful here. It's not just negative 3.616. It's scientific notation, so it's times 10 to the negative 4th. So that means that this is actually negative 0.0003616, so on. So be careful, always look for that scientific notation. Here's B, here's C, here's our constant. And where R squared gives us information about the fit. So we see that our model is negative 0.0004 x cubed plus 0.0401 x squared minus 1.3898 x plus 21.6791. And all of these numbers come from A, B, and C up here. So again, always look for that E because that's going to be your scientific notation. Make sure that you can replicate this and get the same results. Now we can also make a quartic model. And in a quartic model, remember we have a quartic polynomial. And a quartic polynomial is similar to cubic, except our highest degree is x to the fourth. Similarly to what we've seen so far, a quartic model is appropriate if the fourth distances are relatively constant, okay? So now you're going to find your first differences, you're going to find those differences to find your second, you're going to find those differences to find your third, and lastly, you're going to use those differences to find your fourth. So again, it's an iterative process. As before, we're going to use technology. I would not even dream of trying to do this one by hand. And it's going to be right below cubic reg in your calculators, and it's going to look like quart reg. Let's look here. Here, the first thing we want to do is find our first differences, our second differences, our third differences, and our fourth differences. Then we're going to decide what type of model we think is best. So the first thing we want to look at, remember, is that our x's go up by a uniform amount. So here we're going 1 to 2, 2 to 3, 3 to 4, and so on. So we're going up by 1 each time. If we don't go up by that constant amount, remember it's going to mess up our answers. So that's always important to look at. Once we know that's good, we can just look at our differences based on consecutive y values. For our first differences, remember you don't get a first difference for your first one because you don't have a comparison. So 4 minus 4 is going to be 0. 19 minus 4 is going to be 15. 88 minus 19 is 69, and so on for all of your first differences. To get your second differences, you're going to do the same thing, except you're going to use your first difference. So again, we don't have one now for the first two, because this is our first one that we're comparing. So 15 minus 0 is 15. 69 minus 15 is 54, and so on. For our third differences, we have to skip the first three, and then we're ready to look at our second differences. And those differences are our third. So 54 minus 15 are 39. 122 minus 54 is 68. And 214 minus 122 is 92. And lastly, to get our fourth differences, we're going to skip the first four because we don't have reference points. And now we'll see that 68 minus 39 is 29. And 92 minus 68 is 24. So for our fourth differences, we only have these 2 points. Now, if we want to consider what model is most appropriate, if we look at our first differences, those are nowhere near constant, right? So it's not linear. 0 to 15 to 69 to 191 to 405, that's jumping up dramatically each step. So definitely not a linear model. Our second differences do something similar, not quite as dramatic, but not great either, right? We're going from 15 to 214 in 4 steps. Third differences have a nice increase too. It's a pretty hefty increase from 39 to 92 in 2. And our fourth differences in this case are as good as it gets. 29 and 24. Those are roughly equal to each other in the grand scheme of things. We don't see a big trend here. Of course, we only have 2, so telling a trend is pretty much impossible. But it didn't go from 229 to like 130 or anything. The fourth difference is having the most stable changes. Let's fit a quartic because we're pretty confident it's going to be better than the other 3. So just like before, we're going to enter our data into our calculator. This is L1, this is L2. And you're going to do the calc quartic reg. Now it's going to give you A, B, C, D, and E because you have 5 coefficients. Here we don't see any scientific notation, so we're good. So we're ready to just write our quartic model as below. Remember, it's based on A, B, C, D, and E. So that's actually all for this section. Told you it was a short section. But remember that the modeling process is almost identical to everything we've done so far. So very little new information other than finding fourth differences and using a slightly different version in the calc. Just be careful when you're taking third and fourth differences. It's really easy to get lost after first differences, if I'm being honest, right? Do it in the table type format that we have, and that'll help. As always, get some practice. Practice makes perfect with math. You can't learn math without doing math. So get some practice, hold on for the end of the semester, and I think that you'll be just fine. Thanks for tuning in, and I hope to see you on the next one.